Hey guys, we are doing a new section today and I will upload the link for this applet, but I want you to kind of play with it so you know how, the central limit theorem, or you have a better understanding of central limit theorem. So you can create a bigger sample size or a smaller sample size, and you can create a different population proportion. And just pay attention to the x-axis because it's going to show you. And if you generate just one sample over and over again, you're going to see just multiple dots as it's getting an average of this 50 sample. And you can see that it's getting closer to 0.8, but you will see a variation in between because it's a random sample. So there's no guarantee that you're going to always hit that 0.8, which is kind of like your goal, right? And if you do generate samples, what it does is that it generates a sample of 10,000. And then if you continue to click on it, then it's just kind of adding up more samples like by 10,000. And you can show or not show normal curve. And I just would prefer that you see that so that you can see how it fits nicely to the curve. And then most importantly, what I want you to see is that how increasing the sample size changes and does it seem like the smaller sample size fits better with the normal curve or the bigger kind of thing? Once you have explored that in your own time, then you can understand the central limit theorem better. So central limit theorem is basically saying that as your sample size increases, that your distribution will look more and more like normal. So we learned about how to write the normal, which is the n, and then you write mean, and then sigma, right? So if it's a sampling distribution, meaning you have multiple samples and then you average them out to draw the distribution, then your normal distribution actually looks, mean stays the same, but your sigma gets divided by square root of your sample size, okay? So that's something that we need to remember as we try some of these example problems. I'm not going to show you how to put stuff in on a calculator anymore because I think you know how to do that, and I realized this calculator doesn't do what my physical calculator does, which is calculating things on normal CDF. So you have to calculate everything before you plug in normal CDF if I use this one. Alright, so let's look at this problem. It says a study was done in which parents reported the number of important information. The mean age was 3.3. Standard deviation is 0.9. And since it didn't say that it was standard deviation of a sample, you assume it's a population standard deviation. So then it says assume normally distributed, and you got 30 people. And 30 is a large enough sample size that you can assume normal distribution. But you will have a new normal distribution, which is 3.3, same. But 0.9 will get divided by square root of 30 because that's my sample size. So then your new normal distribution, 3.3 will be done. And then it's asking less than 3 years. So here. So you're going to plug it into normal CDF. Lower bound to be a very small negative number or a very big negative number. And then upper bound will be 3. Mean 3.3, and standard deviation is whatever this number is, 0.9 divided by square root of 30. And you get 0.034. So that means there is about 3.4% that this happens. So again, it's not very different from what we've done if we just added a new element of a central limit theorem and how sampling distribution works and how to calculate all that, okay? But we're still using z-score, we're still using normal CDF and all of that. This one, if I read the question, it says the mean is 25 degrees and standard deviation, again, there's no mention of sample, so we assume population. And then normally distributed, and then we chose 20. Again, 20 is big enough. And so it's asking, so our new normal distribution would be 25, 3 over square root of 20, because it's a sigma over square root of n. And my distribution will look like this, and it's asking 26.3 greater. That's what it's asking, right? So you're going to put it in normal CDF again, and then if you do normal CDF, you get 0.026, meaning there's a 2.6% chance of randomly selecting a mean of slope that will be greater than 26.3 degrees. Alright, last one of this kind. It says average age of the cat is 96 months, standard deviation 16 months, and the random sample of 36. This is large enough, so we assume normally distributed situation here. And so 96 stays the same, but the standard deviation is 16 over square root of 36. And this one is looking for 90 to 100. So it's in between. So your lower bound will be 90, and your upper bound will be 100. And then your mean will be 96, and your standard deviation, whatever the 16 over 6 is. Put it in a normal CDF, and you get 0.921. So 92.1%. Okay, so hopefully nothing is too confusing. Normal approximation is another thing that we are going to learn about today. This one is basically you have a binomial situation. So you have only two outcomes. The probability of success stays the same, independent, blah, blah. And just like the large sample size, if you have a large count, so basically the same thing as a large sample size, then you can use normal distribution instead of binomial distribution. And how do we make sure that something is large enough? Well, we check n times p. So your expected value, is it greater than 5? And your expected, failure, is it greater than 5? If they are both greater than 5, then you can assume normal. And then your, mean would be n times p, because that's your expected value. And then your standard deviation is NPQ. Okay, let's go to the example problem. The 10% of the member of a golf league are younger than 30. So I guess my probability of success is 0.1. So then the probability of failure is 1 minus 0.1, which is 0.9. And it said 200 people were randomly selected, so my n is 200, and it's asking for the probability that more than 10 will be younger than 30. So we first need to make sure that NP and NQ is greater than 5. So 0.1 times 200 and 0.9 times 200. Well, since this is greater than 5, and 200 minus, this would be also greater than 5. So then we can assume normal. So we're going to draw normal distribution, but my mean is 0.1 times 200, and then my standard deviation is 0.1 times 0.9 times 200. And then we're going to use, let's draw the distribution. So that's 20, right? And it's asking more than 10. So it's going to be a bigger number. So let's use normal CDF. So your lower bound will be 10, upper bound will be a really large number, mean 20, standard deviation, whatever this square root of number is. And then I get 0.991. I rounded. So it's about 99.1%. Fairly large, yeah. A study found that 40% of all of town citizens approve of a new train station. So then my P, probability of success, is 0.4. If 50 citizens are randomly selected, N is 50, well, Q is 0.6. So what is the probability that fewer than 20 citizens approve of this? All right, so I need to check NP and NQ greater than 5. 0.4 times 50 is 20. So since this is 20, this would be 30, right? Because NP plus NQ has to add up to N. So then we can use normal approximation. So the mean would be 0.4 times 50. And then standard deviation would be 0.4 times 0.6 times 50. And then we're going to use normal CDF again. But let me draw the distribution. For me, this is really helpful because it reminds me where my what do you call it? Where my lower bound and upper bound is. And this one actually says fewer than 20, right? So there is a big chance that this ends up just being a 50% as an answer. Let's see. We'll do it. Like I said, normal CDF gives me 0.5. Once you, when you round it, it actually gives you 0.5. So, yep, 50%. Last question of the day. A baseball player gets a hit 32% of the time. So P is 0.32. And then Q is 1 minus that, so it's a 0.68. Find the probability that the player will get at least 26 hits in his next 100 times at bat. So this one is a little bit more sneaky in a way that it doesn't give you that your sample size was whatever, right? But it says next 100 times. So N must be 100. And I want to know that if this guy hits at least 26, okay? So let's do NP and NQ. 0.3. 2 times 100, is that greater than 5? Yes, it is, because it's a 32. So that means that the NQ would be 68, so we can use normal distribution. NP, 32, which is our mean, and then the standard deviation is 0.32 times 0.68 times 100. So then 32 is here, and it wants to know at least 26, so it's this. So lower bound is 26, upper bound, really big number, mean 32, standard deviation of that thing, and do normal CDF. And I get the probability of 0.90. So 90%. 90% of the time, this baseball player will get at least 26 hits in the next 100 times. That's it for today. I hope this was pretty straightforward, even though I did introduce a kind of a new concept, new theorem. But everything that we have done should be pretty familiar because it's something that we've been practicing for the past section. And the only thing that is changing is that when you have a specific sample size, you are not just using the sigma that is given. You have to calculate a new sampling distribution, new sample standard deviation, which is a sigma over square root of n. If you can remember that, and if you know how to use a normal approximation for binomial distribution, then you should be fine doing your homework problem. AP students need to do a little more than this because they have to always check the conditions and make sure the normal distribution is something that they need to use and so forth. So they need to provide a little more evidence. But as long as you're checking if the sample size is large enough, if it's mean, and if you have a large enough counts for the proportion problem, you are good to go. Okay, guys, I will see you guys tomorrow. I think David sent me 10.4, so I need 10.5 and 10.6, so I'm probably gonna ask someone soon, so yeah.